So it's quite simple, right? Remember the fact that for every red node, both of its children must be black. Therefore, it means that we may have many black nodes along a path, but we can't have too many red nodes. And therefore, on any simple path from root to a leaf, at least half of the nodes must be black. Here's at least half of the nodes must be black. This means we must have more black nodes than red nodes. And therefore, this is certainly true. The black height of the tree must be at least half of the height of the tree. And therefore, the size of root, which is n, is bounded below by 2 to the power of black height of the tree minus 1. And this is greater than or equal to half of h. And therefore, we are done with the whole proof. So we know that a red-black tree is sufficiently good in the sense that although it's not so balanced, but it guarantees that the height of the tree is big O of log n. Then let's check the operations. We start from insertion. A very simple and straightforward idea is that when we make an insertion, first color the new node red. Okay, so the point is we will try everything we can to avoid changing the black height of the tree. If the number of black nodes is not changed, we don't have to do anything to rebalance the tree, and therefore it saves time. So for example, if this is the current tree and the new node is 5, first of all, we simply do a normal binary search tree insertion and put 5 here and color it to be red. And so in this case, we're just done. We don't have to do anything to rearrange the tree. So this is the lucky case. What if we're not lucky? So next, what if we insert another node here? Say the new node is 4. And we begin to check its parent and realize that it violates the red-black property because we have 2 red nodes here. And that corresponds to the case 1, where the new node is red, its parent is red, and its parent sibling is also red. In this case, the solution is extremely simple. Just swap the colors. So the number of black nodes are not changed along both paths, and that solves the problem. So in this case, let's just swap colors. And this local problem is solved. However, we cannot stop because this node was black and we have changed its color to red. So we have to be careful. Whenever we turn any node to be red node, we have to be careful. And we have to check its parent. And if its parent is also red, then that's case 2. Case 2 is when this node is a right child of its parent, and its parent sibling is not red, but black. So this is case 2. In case 2, we're going to have to do one rotation first. Okay, rotate these 2 nodes, and we get the situation like this. But the problem is not solved yet. So in this example, let's rotate 7 with 2 and obtain a subtree like this. Okay, so this is case 3. So what can we do now? We would like to keep 2 black nodes along this path and 1 black node along this path. And the solution is to swap colors and rotate. First, swap colors and then make a rotation. Before the rotation, there are 2 black nodes, and after the rotation, there are still 2 black nodes. Okay, and before the rotation, along this path, there's only 1 black node. It's the same, 1 black node along this path. Apply this solution to this specific example. What do we do? First, swap colors. Make 11 a red node, 7 a black node, and then rotate. rotate 11 down to be the right child of 7 and make 7 the new root. So that is the result. Recall that in an AVL tree, when we make one insertion, there are basically 3 steps to go. Step 1, just insert node into a binary search tree. And step 2, begin to update the BFs from bottom up and check if there's anything wrong. In the worst case, we're going to have to do a double rotation. It's equivalent to 2 single rotations. Okay, so these are the 3 things we must do in the AVL tree. In the red-black tree, the first thing is the same. We have to insert the node into a binary search tree. This step is the same. And in the worst case, we also have to check the colors from bottom up. And in the worst case, we only have to make at most 2 rotations. So the workload is about the same as the insertion in the AVL tree. Oh, well, there are also 3 other symmetric cases. So the overall performance is basically the same as what we have in the AVL tree. It's log n, since the height is big O of log n. And if we carefully implement it using iterations instead of recursions, it can run a little bit faster than the insertion in AVL tree. But the difference is not that significant.